So good morning, everybody. So since I am working at the European Space Agency, I brought some stickers and some things to make your own model of Rosetta here. So you can take what you want and distribute to your colleagues and friends. So solar system exploration, that was the talk that was asked by Hervé and Muriel. So it's a very vast topic and impossible to cover in 3 hours. So that's why I made my own selection of what I wanted to tell you this morning, and I hope you will like it. So during this talk, I will discuss. I will go to many missions of European Space Agency in planetary science, and I will show a lot of images showing some result. And as a preview, I would like to show you 2 images, just to introduce a bit the topic. First, because it's this one is one of my favorite images in planetary science, because I've been working a lot on Mars, and I don't know if you know what it is. I think you should know what it is. What it is? It's the Valles Marineris, the largest canyon on Mars, which is also the largest canyon in the solar system. And I like pretty much this image because it took a lot of time and effort to build this image. It took 5 years for the teams on board Mars Express to make such an image. So I will come back to that later. But I wanted to start with this because I think it's a fantastic image. And from this point to this point, you have 3,000 to 4,000 kilometers. And the height of the canyon here is something like 10 kilometers. The height has been exaggerated. It's a very interesting area on Mars, in particular for geological studies. People will be busy with this kind of topic for the next 10 to 20 years, in particular to understand why do we have such a large canyon on Mars. Another image I will show you later as well. I think to me it's one of the fundamental discovery in the last few years is this one. So I guess you know also this one, what it is. It's the Enceladus, the moon of Saturn, a very small moon on Saturn. And we could not expect that on such small moon we will see this kind of feature, because small moon means no activity in general. So here we see plumes of water vapor escaping from the surface and Enceladus at the South Pole. And that tells us a lot of interesting information on the interior of this moon and also about habitability in the solar system. So I will come back to that later. So that was just a preview of the talk. Also a little bit about me. So I've done my PhD in Grenoble in 2000 on Earth and Mars ionosphere. So I'm a plasma physicist. And then quickly I moved to the European Space Agency in Noordwijk. And I think I was lucky because I had the chance to be involved in many planetary missions. They are listed here, either as project scientist or deputy project scientist. So Cassini, Huygens, then Venus Express, then Mars Express, then ExoMars, and then recently to JUICE. So I think I'm a very lucky person. And then, so the significant part of my work is to manage the science on board this mission, to work with all the scientists involved with this mission to make sure that we got the most of those missions. So it's a full-time job. As you can imagine, we can discuss that a little bit later. But at the same time, I try to continue a little bit of research activities, and I'm still working on plasma physics, interaction between atmosphere and the solar wind. That's the thing I am most interested in. And also when there is no atmosphere, like in the case of Martian moons, there is also an interesting interaction between the solar wind and the surface of planets and moons. And I am also interested in this area. So that's a little bit about me. And the messages I would like to convey during this talk are described briefly here. First, I would like to show with all these images and planets and missions that the solar system is really made of really diverse worlds. When we look at the different planet or moon, we see always something different. And I think it's very interesting to see that. I will try to illustrate. Also, what is important, as I'm pretty sure you had some talks during the week on this topic, is that what we see now, when we take images, when we take data of planets and moon now, this is not the picture that was there 4 billion years ago, because the planet evolved. It looks obvious, but in fact, we understand now more and more this concept, and it's very important. So, and evolution of solar system with time And also we see more and more active worlds. So the Earth is the most active world of planet in the solar system. But it's important also to explore other active worlds, because if we want to study habitability in the solar system beyond Earth, it's better to explore active worlds. So this is also something I would like to show. For some of the mission, I like to show unexpected discoveries, because that's always interesting. When we prepare a planetary mission, we sell the mission with a specific science objective. We want to address a question. But what happens, we need to see whether we address the question properly. Sometimes yes, sometimes not totally. But what happens in most cases, and this is I think the beauty of the work and the exploration, is that we have some unexpected discoveries, and I would like to show some of them. Also, I will discuss a bit the European Space Agency, how to select a solar system mission. Also, I think it's important. When you see images data, as a scientist, usually you don't care too much what is behind. And I will try to explain you a little bit what is behind those images in terms of preparation, selection of a mission, and so on. I think it's also interesting to mention. Also, be a little bit how to manage the solar system missions. And is it worth the money? Because when I give talks, usually in the general public, I've got many questions like, why are we doing that? Why do we invest so much money in this kind of activities? Is it worth the money? So I will mention a little bit this topic as well. So ESA, I think it's important to give the context of ESA and the framework. And the purpose of ESA, so the European Space Agency, is really to provide for and promote for peaceful purposes cooperation between the European member states in the area of space research, technology, and space applications. That's really the main framework of our work. So it's important to remember that. And we will be talking mainly about science, of course. This is what we are interested in. But just for you to let you know that science, it's only a small part of the European Space Agency. We have many other activities that I think it's important to be aware of. So space science is the one we are interested in, but there is also human space flight. So we have astronauts which go to the International Space Station. We are doing an activity called exploration. It's for Mars and the Moon. Earth observation also is very important. Launchers, because we want to send satellites to space. So we have a big activity about launchers. Navigation, I think you will hear about that soon, because we are having soon the European GPS system, which is called Galileo. And now more and more satellites are about Galileo constellation. They are orbiting Earth. And soon we'll get the application with the European communication system. Telecom, of course, it's important. Technology and operations, because it's a part of ESA. We operate our satellite. We don't give that to the industry. So a lot of range of activities. And about the budget, I will not go into all the numbers. It's not very important. But just to know the overall budget of ESA per year, which is something like 5 billion euros. So if you compare with other budget expenses, etc., you can get your idea whether it is small or is it big. And after the talk, maybe the idea will be to check for yourself whether this is worth the money. So what we do with 5 billion euros per year, is it interesting for Europe, for us, etc. And all the member states, they contribute at a given percentage. So we have big countries like France, Germany, and Italy, and otherwise all the other countries. In fact, there is a minimum requirement to give a budget to ESA for each country. And otherwise, the member states, so each country is free to contribute to certain programs. So some countries are more interested in some special activities. So that's why the percentage is also different, and that depends on the size of the country. We cannot expect a small country to contribute same amount as a big country. So that's also interesting. And we have, because we are European Space Agency, we have different sites in Europe. So the one I am working in is in the Netherlands. But we have the headquarters in Paris, and we have big centers in Spain, so close to Madrid, in Italy, close to Rome, one in ESOC in Darmstadt, close to Frankfurt. We have also the European Astronomical Center in Cologne, and a few other small centers somewhere else. So it's really spread over Europe. And where I am working is the STEC center. So you see the size of the centers. You see the cars here. It's quite big. We have almost 3,000 people working here, close to the sea. A big center. And what is important to mention here is this part, because that's where the satellites are tested before they go to space. It's important to test satellites. You don't send a satellite just directly, you put it in a rocket. First, there are a lot of tests, and the tests, they are being done here. So, and just for the little story, when I started at ESA 15 years ago, I was lucky because the Rosetta spacecraft was there for more than a year for integration, testing, and things like that. So I was there every day or every week to see what was going on. And it's very interesting to see all the tests possible, and in particular, the one which was the most interesting was the deployment of the solar panels, because you have seen the big solar panels on Rosetta, and to see the test of the deployment in real time, it's quite something that you remember. So that's where I work. So now let's back to the talk, solar system. So I will not explain you all the planets where they are. You know that, no problems. So we'll go through some of the planets here, not all of them, because again, no time. I like this view graph for a very specific reason, because at the time, 10 years ago, I was working on Huygens. You know the Huygens probe, a big discovery, a big impact on the public. And a few weeks after the arrival at Titan, we got a special request that the French president was very much interested to know more about the result of Huygens. And he wanted to have a special meeting in his palace in Paris with some scientists to explain. He wanted to get an explanation on the Huygens. At the time, it was Jacques Chirac. And so I prepared a view graph for this presentation. I was not invited myself. Unfortunately, I was not high enough in the hierarchy. But I prepared the slides, and I prepared these slides that people should explain to Jacques Chirac the solar system. And I was told he liked very much this slide. So that's why when I give a talk, usually I show this slide to remember this interesting moment in time. So the same slide, but now with all our European planetary missions that we have done so far, just to tell you that we have a very ambitious program that we should be all proud of. So all the missions are listed here. For example, for the Sun, we have SOHO, Solar Wind, Ulysses, Solar Orbiter is in the making. Bepi Colombo is the future mission to Mercury that will be launched in a couple of years. Then we have a lot of missions. Venus Express for Venus ended last year. Smart One for the Moon and ended in 2006. Cluster is for the Earth's magnetosphere. Proba 2 is to observe the Sun. Giotto was one of the first missions in planetary science to explore the Halley comet. I will talk about that a little bit. Mars Express to Mars. Rosetta for the comet and landing on the comet. Huygens, I mentioned, landing in 2005 together with Cassini. Cassini is the NASA mission, but it's a collaboration with ESA. We still have some ESA participation in that. And the next mission to the outer planet, JUICE, the one I am working on, so launch in 2022. Also, I will discuss this mission. So I will go through a few of these missions in the next slides. But first, how to select a solar system mission. I think it's not a topic which is not well known, and it's important when you are studying a mission. In fact, there have been a lot of work before just to get the idea, to study the mission, and to select the mission. So I wanted to briefly mention that. And the main message here is that it's really a bottom-up approach. So the ideas and the work, it's really come from the scientific community. So you now or later when you get a position to work in planetary science. So what happens usually is that we issue a call for a mission. We say, you have 3 months to propose us a mission, which we have a budgetary envelope of 500 million. So what do you want to do with 500 million? Send us the idea, and then we will select a mission based on that. So the scientists, they have 2 to 3 months to prepare a proposal with large consortiums. and they submit the proposal to ESA, and then there is a lot of work with meetings, committee that we call working groups in different areas, and those working groups they include scientific from the science community, and then they study the proposal, and they make recommendations to ESA, and then ESA discuss with the body which really decide. That's the political body, the Science Program Committee, made of representative of each countries from ESA, and they decide based on the recommendation from the scientific community. So when we got a call, we got maybe 30 proposals, and we keep maybe 3 or 4 for studies, and this is what ESA will decide. At some point we say, okay, we have three ideas, we will study them in parallel. And then it takes a few years, and then we are back after the end of the study. We need, because from 3 missions we need to select only one. We can only fly 1 mission at a time, and then we go back to the scientific community to say we have those 3 missions, which one should we select? And it's a tough decision because many people have been working a lot, putting a lot of effort to submit the idea and to work on the mission, and at the end, from 30 to 3 and from 3 to 1, it's a tough decision, but that's how it's done. It's really a bottom-up approach, which I think it's quite good. And the selection criteria, it's always very complicated to select a mission because you need to compare the different missions. And of course, the science is the main criteria, but also is it possible to make the mission, technically speaking? Because if a mission is not possible to make at this time, we cannot select it. Otherwise, it's problematic. Also, does the mission serve a big community? Because we cannot select a mission every year, and we cannot serve all the topics in science, because we're also dealing here with not only solar system but astronomy and fundamental physics, and we cannot have a mission in this topic every year. So it's difficult to serve all the different communities. So if a mission will serve a broad community, usually we prefer. But so that's, and the last criteria is also the price, because we say we have a certain budget limit, and is this mission fit in the budget? Yes, no. If it's no, the mission will not be selected. So that's a lot of criteria that makes the things a little bit complicated at this stage, and also at this stage, because at this stage it's politics, budget, and that's it's always complicated. So let's now have a look at different missions. I think the first planetary mission of ESA was really this Giotto in 85, 86. That was the flyby of Halley comet. I don't know if you have, maybe you were too young to look at it, but that was a very interesting moment, because that was the very close flyby at 600 kilometers from Halley comet. And the main output of the mission was really the high resolution of this nucleus, for the first time the nucleus of Halley comet, and also the study of organics molecule. This is the most important part of how we do want to explore comets, because they are really pristine material of the solar system. So this is how you will look at the solar system, how it was 4 billion years ago, and we want to understand these bricks and the solar system. So, and there are a lot of organics material which are interesting for the habitability point of view. An interesting aspect of this flyby is that it was in March 86, and it was part of a multi-mission approach, because it was not only Giotto which flew by the Halley comet here on the 14th of March 86. We'll celebrate the 20 years soon, by the way. Many other missions. Here you have the Vega spacecraft from Russia, but there were also Japanese and American spacecraft. All in all, it was a fleet of 6-7 spacecraft that didn't want to miss this pass of the comet, because you know that Halley comet comes only every 76 years. So that was we didn't want to miss this time, otherwise we have to wait many years. And the interesting aspect is that all the other missions, they made measurement, of course, of the comet, but there were a large uncertainty in the position of the comet. So to all those previous missions that flew by Halley a few days before, in fact they helped to better pinpoint the position of the comet, and to allow a very close flyby at 600 kilometers from Giotto. Without the previous mission, it would have much more difficult to have a very targeted flyby. So that's why it was a very interesting collaboration, international collaboration of many missions, independent from each other, but at the end they work together. So I think that was a very interesting part. And Giotto was also special because normally that was the end of the mission, so flyby of Halley, and then that's it, we are done. But then we find that given the orbit, the trajectory of Giotto, we could visit another comet. So it visited another comet 6 years later in '92, and it's not possible for me to say the name of the comet. You can find it on the web, but it's a name which is just very difficult to pronounce. So I will not tell you the name of the comet, but if you are interested, you can find it on the web. But from '86 to '82, that means a few years in space. And what ESA has done, and it was not planned at the beginning, is to hibernate the spacecraft to make sure it can stay 6 years and then do the mission again to another comet in 1992. And that was not planned at all to have a spacecraft which hibernate, and we did it. And then that was used for Rosetta, because Rosetta was put in hibernation for 2 years, but that was planned from the very beginning. But here it was something which was unplanned, and it worked quite well. So that was for Giotto. Then after Giotto, the next mission launch was the Cassini Huygens, was launched in 1997 and arrived at Titan in 2005. And that was a very interesting mission because we wanted to explore Titan, which is the largest moon of the Saturn system. And Titan, with this thick atmosphere and methane cycle, it's a very interesting target for astrobiology to study whether life could arise in another place in the solar system. So for astrobiology, Titan, it's a very interesting place. So that's why it was decided to build this little probe called Huygens, and it was attached to the Cassini spacecraft. So Cassini went to Saturn, and then it delivered the probe into the atmosphere of Titan. And you see the heat shield here, which decelerate the probe from a few kilometers per second to a few hundred of kilometers per hour. And then a series of parachutes, 3 in total, which slowly decelerate the probe to give enough time to study the atmosphere, because the main goal was to study the atmosphere, and the descent was something like 2.5 hours. And then it was landing on the surface, and we got 30 minutes of data on the surface, and that's it. No more, because the Huygens probe was running on batteries, and at some point the batteries were depleted, and there were no solar panels. At this distance, it does not make sense. So it was a short mission, because 3 hours, and the mission was the idea was submitted in 1978. It took a few years to study, to approve, with all the selection I was mentioning. And then it was launched in '97, 7 years in space to go there, and then 3 hours of measurements. So when I was working there, my manager, so Jean-Pierre Le Breton, the project scientist, has spent maybe 30 years on his life for these 3 hours of data. So that means the amount of data is not which is always interesting, it's what it is for. Those 3 hours of data, they really change our view of Titan. So some views of the probe. So this is the Cassini spacecraft. So you see the size compared to people here. So it's a big spacecraft, 5 tons, the big Huygens antenna, and the probe was mounted here. And you see another view of the probe. That's the heat shield, which protected the probe from the entry in the atmosphere at 6 kilometers per second. You have a strong deceleration, and you need to protect the probe. So to protect the probe, you have this multi-layer insulation. But what is more important is you have the heat shield, which is made of special tile, which will protect the probe from the heat. Okay, and I don't know if you have an idea about how those tiles are made of, or what it is. And by the way, little anecdote: those tiles were built here. They come from EADS Bordeaux, so it's not far from here. So because nobody knows a lot about those tiles, I decided to bring you a tile. this is a tile. So you see, that's the same. So I will circulate it to you just for you to see. It's quite light, because when we send something to space, it has to be as light as possible, because the kilogram of something launched to space, it's quite expensive, and at the same time it has to be light, and at the same time it has to protect, it has to do its job. So I will circulate it, you can have a look. That's based on the industry from Bordeaux, and because it's industry, we cannot say what it is. It's a secret from the industry, and we don't know what it is. But it's based on the missile technology. So another view of the probe here. You see the tile, the cover, and the probe inside that was protected here. And on the probe there were some spin vanes that were there to make sure that the probe will rotating in the atmosphere, because here we have a camera, first for the stability of the probe, but also there is a camera here, and we wanted the camera to take pictures in different directions. And to take pictures in different directions, you need the probe to spin. And for the probe to spin with the atmosphere, we had some spin vanes which were inclined at a certain degree to allow the spinning of the probe. And what was interesting and not quite fun for the project after all is that the spin vane, they were mounted with a certain design here to make sure that the probe will turn in a certain direction. And then all the instruments, they took this into account to analyze the data. And what happened is that when the data came on ground, the scientists could not understand what happened to the data. There was something weird, and they found out that the probe was not turning in one direction, but spinning in the other direction. And that's something 10 years after, we are still not quite sure about why. We have some ideas. We have done some additional tests, but it looks like the spin vanes, they did not work as planned. So this is, again, 10 years after, we are still working on this issue. So why we have been to Titan is, and as I said, the idea came in 78. Just to give you the time scale of a mission, it can easily be 20, 30 years. Because in 77, 78, there was the NASA Voyager, which flew by Saturn and Titan, and they took this picture, and they took some measurement. And it's a very intriguing body, because we could not see the surface, because the atmosphere is thick. There is haze in the atmosphere, aerosols, which prevent to see the surface. And it's always annoying when we want to explore a planet or a moon. We want to see everything, and we want to see the surface. And also it was discovered that there are many interesting organic molecules in the atmosphere. So from this image and this data, there was the idea to come back with the Cassini and Huygens mission more than 20 years later. So that's because of these images that we had this Cassini and Huygens mission. And then, 20 or so years later, even more, 27 years later, the Huygens probe descended in the atmosphere of Titan. It was on the 14th of January 2005. And we were all in one of the center of ESA I mentioned in Darmstadt, close to Frankfurt. That's the main control room to control all the satellites, so all the screens, all the computers. And we were all here waiting for the data. And the mission happened in the morning of the 14th of January, so 3 hours. But then it was not a real-time mission, because we could, given the distance, we could not get the data real-time. Because by mission design, the data were first sent to the Cassini spacecraft, which was flying over Huygens, a few tens of thousands kilometers above. And then, during the mission, the 3 hours, Cassini was listening to Huygens, get the data. And then, after the end of the mission, Cassini continued his orbit around Saturn and then sent back the data. And given the distance, it took some times. So the data came finally on ground, something at 5, 6 o'clock in the afternoon. And I can tell you that people were very excited by that. And a few hours later, we were in this control room just to have a preview of the first images of Huygens. And this is the pictures that were taken in this control room, because 3 images were displayed on the screen for the scientists. And I can tell you that was a very emotional moment, because people were waiting for that for 27 years. Just a few hours after the data arrived, we showed the data, the images with no correction, you see that it's really uncalibrated image, black and white. And that was very emotional to see this kind of landscape and all these channels here, which are due to the methane cycle on Titan. And I remember I was also in this room, and people were just speechless. And also, at some point, there were no Twitters or things like that. And in fact, the journalists, they were calling the people inside. And the people, they were on the phone, and they could not tell a lot because they could not say it. They didn't have a lot of words to explain what they were looking at. So that's why really I have also another very emotional moment, which was quite something to remember. After maybe 1 year later, you can see the difference in the data analysis from this raw image, those raw images that are just coming from the telemetry, and this kind of landscape, which is a collection of the individual images. So these are the channels, for example, the channels that we see here. They are here. So usually it takes a year to build this kind of nice images, so landscape with the color. The color comes from spectrometer because the images are in black and white. But then we have spectrometers which works in the visible infrared, and then you can reconstruct a kind of color of these images. So after the mission, the Huygens mission was over, Cassini was still operating, and it's still operating, by the way. It will start to work in 2017. And after we were following the Cassini mission, so I just will show some nice images. So the beauty of Cassini, it can take images when the sun is behind Saturn, and you can have a beautiful view of the rings and even the far distance ring here, which otherwise are very faint to see. And we can see also some planets, and in particular our Earth here. So it's always I don't know how to say, emotional or inspiring to see our little pale blue dot here. So we are there. I was talking about unexpected discovery, and so Enceladus, so the little moon, the 500-kilometer moon around Saturn, is a very interesting body, and I think it's one of the most interesting discovery of this mission. And usually what is interesting in that case is that this discovery was made not with imagers or spectrometers, something that it's easy to find something and make discoveries. The discovery I will be talking here was made with the magnetometer data. So I will explain. So we have a magnetometer data on board Cassini because of the large magnetic field. So the magnetometer is used to understand the magnetic environment at Saturn, and it's like Earth. There is a dipole, which is in the case of Saturn is very strong. So there is a dipole, and the interaction between the environment and the magnetic field is very interesting to understand. There was a flyby of Enceladus from Cassini, and what they find is that the magnetic field was disturbed around Enceladus. And that was not expected at all, because we didn't know that there would be something very exciting there. And the deformation of this magnetic field line indicate, that's how the data were interpreted, that there is an atmosphere around the moon which in fact deflect the magnetic field. And based on that, they decided to go even further and then to take additional measurement with mass spectrometer and images to see what's going on, because that was really unexpected, and we wanted to confirm this data from the magnetometer. Because people say, oh, what it is? It's really weird, it's not possible. Because it's a place, there should not be any atmosphere around this small moon. And at some particular flyby, this is what we have seen, what I've shown at the beginning, these plumes that are escaping from the south pole of Enceladus. And they are, by looking into more details about this feature, in fact, we find that there is water vapor. So that's very interesting to find water, because water is always the ingredient of life. So it's always interesting to see water escaping from the moon. So that was a beautiful discovery and completely unexpected from the Cassini mission. There were additional flybys and data taken that allow the scientists to study the interior of Enceladus, but by doing what we call a gravity experiment. So in that case, we don't take any picture. We study when there is a flyby, we send a signal to Earth, the telecommunication signal, and we record the Doppler effect at Earth that allows to reconstruct the trajectory, the velocity first, and then the trajectory of the spacecraft. And when there is a flyby, which in principle we try to have as close as possible, then the little change in the trajectory of the probe indicate something about the interior, because the trajectory is deflected due to the internal gravity field. And the little movement of the spacecraft can be related to the gravity field of the body, so in that case Enceladus. It's a very precise measurement. Just to give you an order of magnitude, the change in distance of the spacecraft can be a few centimeters or just a few meters. But all this little change will tell us something very interesting about the interior. And in that case, those gravity experiments were used to try to match the data with the possible interior structure of the moon. And the data, they are really compatible with this kind of structure. So you have the moon, the surface, you have an ice crust here, you have a core here, and here there is an ocean. In that case, it's global ocean because it's everywhere, of a 10 kilometer deep, something like that. And the ocean here is in contact with the surface, and that's why you have this plume here. So you see we have magnetometer data, we have images, we have gravity data, and all these data give now the big picture that there is something very interesting going on in Enceladus. So when I was talking about call for new missions, now when there is a call for new mission coming out from NASA, from ESA, Enceladus is always a prime target because we want to go back. Because every mission makes a step, we find this, and then the next mission we need to understand that in detail. So for example, the next mission could be a lander to land here and to see what's going on. That could be an example. So that's how we process in the scientific community. So to me, it's one of the most intriguing discovery, I think, in the last 5 to 10 years. Titan lakes. So Titan, go back a bit to Huygens. So that's the hazy atmosphere. Because of the methane cycle, we foresaw the presence of lakes on Titan, ethane, methane lakes. And in fact, the Huygens probe was designed also to land or to sink, I don't know how to say that, on the lake. The equipment was also there to measure something liquid. Unfortunately, we didn't find any liquid surface, but that was foreseen and that was expected. So Huygens didn't find any liquid surface, but Cassini, with his multiple flyby and 10 years mission, find evidence for lake, and one with the camera or spectrometers, I don't remember exactly, but you see a reflection here, which is due to the very flat surface, and that was one of the evidence that there are some lakes here on the surface of Titan. And then with the radar, which is on board Cassini, there were much good coverage of the surface, and in particular the North Pole, you see many lakes here made of hydrocarbons. So that was also an interesting discovery. This one was in fact expected. We wanted to discover liquid surface on Titan, so this is the case here. But what was not foreseen before, and that was due to a fine analysis of the radar data, is that for some of the lakes, we were even able to probe the depth of the lake. So it's always good to see that there are lakes, but then the next step is to find how deep they are. And that was also good publications here, that you see the depth of the lake here. That's the radar path in the middle of the lake. And you see it's down to 160 meters deep. So it's quite a large lake. Huh? So I think that also was an interesting result of the Cassini mission. Then moving, so I go back to inner solar system now. So Mars, in particular Mars Express. So Mars Express was launched in was approved in '97. And the idea, so this image, you have to consider, it took 5 years to make it, because when it was taken with Mars Express, the Mars Express camera, the high resolution camera. When you take an image, you take an image in this area, for example. because we cannot take images all the time with Mars Express. Mars Express has a very elliptical orbit, so we need to take images when we are closest to the planet, because from far we don't have enough resolution. So we can take images only on a few portions of the orbit. So if we are in the orbit there, we take this image, but the next orbit, the image will be here, the next orbit, the image will be here, and so on. And also we need to take images when we have the sun, and sometimes we pass over the canyon when there is a night. So and then in that period we cannot take images. So to make this mosaic made of a few images, it took 5 years, because we cannot take the image all the time when we want. Yeah. And so that's why I like these images, because it really took a lot of time in the planning. And if the image was there, we know that we needed another image there. So that means the people doing the planning, they were studying at which orbit can I take the images that will allow me to continue the mosaic. And that takes a lot of time in the planning, because people look at the orbit, when the illumination is okay. And then when we take images, we need to have clean conditions in the atmosphere. Sometimes there is a dust storm, so the images are not usable. Then we need to wait 1 or 2 more years to go again above this area. Just to tell you that when you look at these images, behind there is a lot of work. So that's what I wanted to say here. An interesting discovery of Mars Express that I wanted to share, I don't know if it's well known, but it's this one. So that's an image, that's the flank of the Olympus Mons, the largest volcano. So the volcano is here. To give you the size of the volcano is like the size of Germany. Okay, so it's a large volcano. And this is the flank. And we find in images this feature. And scientists doing geology, they like very much to do comparative studies between planets and our own Earth, because of course on Earth we know the geology and we have a lot of information. So it's always good to compare features that we see on Earth to see if we can say something interesting, meaningful on Mars. And if you compare this feature with Earth, there is an interesting comparison between, for example, glaciers in Antarctica. And you see from this feature, you can see that here it's very possible that it was a glacier at Mars. So that was the first thing. So discovery of a possible glacier at Mars. So that's already a discovery in itself. But the other interesting discovery is where those features are. So if you remember the location of Olympus Mons is here. So it's not far from the equator. So usually glacier, we would like to see glacier, we would expect it to see glacier here or here, because of the climate and things like that. So that means that there was some climate changes at Mars, and to interpret this location of this glacier, given what we know about the condition of the atmosphere and climate on Mars, it was interpreted that the rotation axis of Mars changed with time, and then the climate also changed with time. So that means the glacier that were at this particular latitude now, they were not at this particular latitude when the glacier were there. So that means it's a sign of change of obliquity and change of climate. So these images can tell us something about the past evolution of Mars, and I think it's also quite interesting to note. Here about the volcanoes, also an interesting discovery. So you have the volcanoes here, so Olympus Mons and the 3 big volcanoes. Also, it's an interesting observation that the volcanoes, they are in a line here. And for some people, it'll remind what happened in Hawaii. But it's not as simple as Hawaii. But the story of volcanic activity, it's quite an interesting topic of investigation. So we take images of volcanoes. And these are the caldera. So here it's Olympus Mons. This caldera is here. And for example, Arsia Mons, it should be maybe this one. Yes. So we take images of the caldera in details. And you see some craters. And as you told me just before, if we manage to count the crater, we can manage to get the edge of the surface. And with the edge, we can define the history of what happened. And this is the relationship between crater counting and edge is given by this empirical law that will not go into the details, but to to be quick, the more crater, as you know, the older it is. But in practice, we have some complicated law that were calibrated using lunar rocks. Because we got back samples from the moon, we could date the sample and we can relate to the number of craters in the moon. And we applied these laws that were done at the moon, we apply them to Mars. So that's what we do. And you see here the edge of some of the surface. For example, if I take this one, Arcia, the edge here is 130 million years. So that means there was some volcanic activity 130 million years ago. For this one, for this particular one, it's here 1.6 billion years. And you see different years. So what does that mean? That means there were different episodes of volcanic activity, which is interesting. So we find maybe 5, 6 different episodes in the history of Mars. So that's interesting to study the history of the planet. One thing. And the second thing is that some of the area, they are quite young in terms of geologic ages. For example, here it's 100 million years. And 100 million, if you compare to 4 or 5 billion years, it's young. And what is not written here, but in the flank of this volcano, there are even some area which are not 100 million years old, but maybe just a few, 2, 5, 10 million years old. So that means there are some very young volcanic areas that were active at Mars, young in terms of geologic scale. But 10 million years in terms of geology, it's like yesterday. So that means tomorrow we can well have a volcanic eruption at Mars. So that was also a very interesting discovery that was made a few years ago with Mars Express data. Something about the spacecraft now, just a small digression to come back to my work, how I manage the mission. You have seen all these images. I told you that there is a lot of work behind in the planning. When do we take images? When do we take all the data? Because what we need to know, or you need to know, is that the spacecraft, we have limited resources. We cannot do whatever we want with the spacecraft. It's just, and we have some limitations that I've listed here. For example, the power. We don't have unlimited power. We have small solar panels. We have batteries. And just to give you an example, on Mars Express or a small spacecraft like that with 7 instruments, we have 500 watts for the whole spacecraft. It's not a lot if you consider the number, 500 watts. If you consider your lamp in your room, which is 50 or 100 watts, we have for everything on the spacecraft on Mars Express, we have 500 watts. And for JUICE, the mission I am working on now for Jupiter, we'll have 1 kilowatt. So it's not a lot. So that means not all the instruments can work together. So that means when we do the planning, we have to select and we discuss with the scientist, for this orbit, I want to observe this volcano. That means the other orbit, another instrument will do something else, because not all the instruments are interested in volcano. There are some instruments that are interested in the atmosphere. So that's why we need to do this planning, taken into account all the resources, and power is an important one. The data volume as well. We cannot take as many images as we want because we have a small antenna and we send the data to Earth at specific time, not all the time. We need to have a ground station on Earth which is there to receive the data. So all in all, it's a complex process. That means that for Mars Express, we can download between 1 and 3 gigabit per day. And for JUICE, the plan is to have at least 1.4 gigabit per day. And the instrument, they can generate much more. So that's why it's always complicated, because every instrument wants to operate. And if we put the planning, the timeline, all the wishes of the instrument teams, we exceed the power, we exceed the data volume. So we have to make a discussion, and it's quite an important part of my job to coordinate that. And sometimes, when there are very important objectives of a mission at a given time, the discussion can be very intense, because we need to make sometimes a decision which will not make everybody happy. And also the pointing, it's important, because sometimes the instrument wants to point there to the volcano which is behind, the instrument there on this platform. And sometimes the instrument wants to point on the atmosphere layer here, and we cannot point at the same time here and in the other direction. So that's why we need also to discuss which pointing at specific orbit are we going to decide, because that will drive the measurement. And the instruments, they are there, and sometimes here we have below here we have the antenna, and sometimes for specific measurement, for example, what I was mentioning before, the gravity experiment for the Enceladus flyby, we need to point the antenna to the Earth, because we want to send the signal back to Earth. So that's why the spacecraft will be pointing to the Earth. And if it's pointing to the Earth, necessarily it will not be pointed on the surface of Mars. So that's will be very rare. So that's why it's important to know that we have some resources on every spacecraft, and we need to discuss how to best use the resources of the spacecraft and of the mission. Yep.
What are the sticks and the picture?
Come back a bit on the science. Also for Mars, what's important is the story of water. When we send a mission to Mars, it has to be linked to water somehow, because water is very important. And there is the idea that there are many information coming from images, coming from mineralogy, that there was liquid water on the surface. I think now that it's a known fact. Now we don't see any liquid water, but in the past, there was liquid water. I think that's something that now is pretty clear. So where was the liquid water, and at which time? This is the main question that we would like to answer. So that's why we send mission to Mars. And one interesting aspect I wanted to show is again, it's a comparison between Earth and Mars. And Earth, we have a delta here. So here we have the water. And you see a similar image on Mars. And I think it's quite striking. It looks like very similar. So that means the idea is this a delta on Mars? That's the question we want to address. So when we see that, we compare that and we say, yes, it's possibly a delta. But it's just from images. But this is only what we can do. And then the interesting part is where do we find those delta? And it looks like the delta, they are quite located in around this boundary that I mentioned before, this Mars dichotomy. So that means it's compatible. That does not mean it is true, but it's compatible with the fact that if there was liquid water, it could be in this area, in the blue area, and the delta, they are the boundary between the water and the land. So that's a possibility that people are arguing in the scientific community. So if Mars was a blue planet in the past, we could have such an images, which is not probably the right one, but that could have been. So the ocean here. And if you look at the altitude distribution on Mars, so this is the North Pole, the South Pole. So as I said, the green area is higher than the blue area, if you remember the one of my slides before. So an ocean or water could have been there because of the altitude. The water goes where it's below, of course. And we could have a shoreline here and a continent here. That's a possibility. It's being argued a lot in the scientific community, I can tell you. But what is clear that there were liquid water in the past. And in the most distant past, in that maybe in the first billion year of the history of Mars, before the big landscape were formed, before the big canyon, before the volcanoes, Mars could have resembled to these images, so a lot of craters and water everywhere. This illustration is the result of an interpretation of mineralogical data with Mars Express. So that indicates that there were liquid water in the distant past, like 4 billion years ago. And that could well be an image of Mars 4 billion years ago, and it's quite different to the one we see now, of course. Another mystery, you may have heard this one. It's the methane on Mars. And so that came from Mars Express and also from ground-based measurement, and recently from Curiosity, that they have detected some, so the red spots, some sign of methane. The red spots mean localization of methane on the surface. So that's the latitude, so close to the equator, for example. In 3 areas, that's for ground-based observation, and the red means the amount of methane in the atmosphere. So red means we find some methane. And that's quite controversial because on Mars, given what we know about the atmosphere, the UV fluxes, we should not have methane. That's just the fact. Because methane is rapidly destroyed with a reaction with water, and there is water vapor in the atmosphere, and also destroyed with UV radiation. So if you consider these basic mechanisms, if there is methane somewhere, it should be destroyed in 300 or 600 years. So that means if we make observation of methane, there should be no methane because it's being destroyed. So if we find methane, that means that there must be an origin for this methane. And this is why the scientists are quite passionate at the moment, because the two possible sources of methane is one, geological activity. So there are some reactions between rocks and water in the subsurface that could generate methane. And the other hypothesis is, of course, the microbial life, which generates also methane. So that's why people are very passionate, and they say that it's not possible to have methane on Mars. And one of the source of methane that was discovered here is here from Mars Express images in false color. It's an interesting geological part which is called Nili Fosse. So that could be related to processes below the surface. But again, it's really a mystery. And when we had some discussion about that, it's always resulted in a very heated discussion in meetings and things like that. Because it's really, I think it's half of the scientific community is think there is methane, the other think there is no methane, it's not possible. So it's always an interesting topic when you bring that to a meeting. So, and even more recently, because with MSL Curiosity, the rover, first they published that there is no methane a few months after the mission. There was even a press conference to announce that there is no methane. So imagine you make a press conference to announce a known result. That's quite interesting. And then a year later, another press conference, another paper that there is methane now. So you see, it's quite interesting. And that's one of the reasons we have built ExoMars Orbiter that will be launched next month to see if there is methane. So let's see if we find a solution to this mystery. And it is not this, huh? Okay. Well, I think we are clear. So now the Martian moons, also an interesting topic, and that's where you will see that the elliptical orbit of Mars Express is quite interesting for that. So we have Mars. We have two tiny moons, so Phobos and Deimos. It's something like 10 kilometers. I don't want to say diameter because they are not spherical moons, but there are small bodies in this range of distance. And this is an image from Earth, where you see Phobos here and Deimos. So the revolution rate of Phobos is 7 hours. It's 6,000 kilometers from the surface. And Deimos, it's 30 hours. It's 23,000 kilometers from the surface. So they are small. Is it interesting to study? Let's have a look. And this is an explanation why we can fly by. We can do interesting flyby of Phobos with Mars Express. So we have Mars, and the two moons, they are in the equatorial plane of Mars, and they are circular orbit. Okay, so you see the orbit of the two moons. And Mars Express, you see the elliptical orbit. And the interesting part is that the elliptical, the plan of the orbit, the plane, which here is the plane of the wall, the plane move. That's celestial mechanics. So it's not always this plane, but the plane move. And at some point, you see that Phobos is doing like that circular orbit, and Mars Express is doing like that elliptical orbit. And at some point, they meet. And that you will see in this animation. And to be able to be there at 600,000 kilometers from the surface, you need an elliptical orbit. With a 400 kilometers orbiter, you will never be able to meet Phobos. So that's an example. So you see the orbit of Mars Express, you see Phobos. And this meeting, because of the two orbits, happens every 5 months. So you see here, they meet. Yeah. We cannot go close to Deimos because Deimos is much further away. But that's interesting. So every 5 months, we can plan a flyby. And of course, we need to be careful because we want to plan a flyby. We don't want to plan a collision. Okay? So that's also something we need to take care. So there is a orbit determination. And if there is a risk of collision, we make a maneuver to make sure we will not collide. Because statistically speaking, with the two orbits, one doing that and the other doing that, statistically speaking, at some point they will collide. And in fact, at the end of the mission, when we have no control of the spacecraft, at some point it is clear the spacecraft will collide into Phobos. We don't know when. The probability is 1 after 1,000 years. So in 1,000 years, Mars Express will be crashing Phobos. I think that's clear. And that's the same flyby, but in closer view. Just to see, first, it's a real orbit. So what happened here happened during this orbit number 7915. It was in March 2010. So all what you see is the real movement of the spacecraft, real everything. So first we were doing observation of the North Pole. This is the North Pole. And then 1 hour later, we go close to Phobos, which is at 6,000 kilometers. And you see the planning. You will see how the spacecraft rotate. Everything was designed beforehand. So everything has to be very precise because the flyby just happened in a few seconds. Because the velocity is a few kilometers per second. So you will see so now we have done the observation of Mars, and then now we will move the spacecraft slowly to Phobos. We have the special commanding of which instrument will be working, because not all the instruments can work at the same time. And then you will see Phobos coming from here. It's very quick, you will see. We just have a time for a few images, a few radar acquisition if we switch on the radar. So Phobos, now we point up, Phobos is there. We take the images, we slew the spacecraft, and it's done. And then after, we point the antenna to Earth, and we send the data, and we look at what happened. And if something wrong happened, it's too late, because you see, it's gone. So it has to be very precise, because then if we miss something, we need to wait for the next flyby, which is in 6 months after. So, and the planning is very precise. And so I will show the next image what happened when we did a bad planning. Okay, so bad planning is this. Because we wanted the Phobos in the middle of the image. There is no point in just, we take just half of Phobos. No, no. It was not made on purpose. It's because we pointed here, and there was a mismatch of 2 seconds. And in fact, it was a planning problem. It's because when we do the planning is done a few months or a few weeks before, because everything is planned in advance. So we do the planning with the trajectory information that we have at the time of the planning, but the trajectory change with time because of the gravity of Mars and so on. We always have to update the trajectory of the satellite because it's changed a little bit. When we do the planning with an orbit, 2 months later, the orbit can change a little bit. And this orbit has changed by 2 seconds. So that's why, and we did not took into account this update in the trajectory properly. So what happened for this is that the people, they got the data on their computer and they look at that and they are not happy. So what happened is they call me. So, and I got for this particular image, I got a serious call from the leader of the camera, and he was really unhappy, I can tell you. Anyway, so that's part of my job. So anyway, it's still interesting. I mean, at least we kept half of Phobos. So that's when we do distant flyby. So that's just for the aesthetic because it's Phobos flying above the atmosphere of Mars. I kind of like this image. But this is the distant flyby, and when we do close flyby, we have all these images. If you look on the web, we have a lot of images from close. It's quite nice. So this is Phobos from maybe here 150 kilometers distance with a good resolution. So for doing geology, it's quite interesting. You see the big craters here. It's a Stickney crater, which is 8 kilometers in diameter. You see a lot of craters, so you can really study the possible history of the moon. And basically, there are 3 mysteries of Phobos which are still not solved. The first one is these features, linear features, which we call grooves in the geological jargon. You see here the grooves, here, here. And in fact, there are grooves everywhere. And the question is why do we have grooves? And in fact, people are not, we don't know the answer. We don't know exactly why they are there. And it's an interesting topic because there are many explanations. One of the explanations is that when this crater was formed with an impact, you can imagine the impact, a big impact, because the size of the crater is big compared to the body. There were a lot of rocks which were excavated from this impact, you can imagine. And then those rocks, they could have been ejected and created those features, because some of the groove they seems to originate from this crater. So that's one of the possibility. Another possibility is that related to the origin of Phobos is if it was an asteroid which was captured by Mars, maybe during the capture, because of when you get into the gravity, and because of the interior structure, the move could have breathed or at least changed his size or something like that. So that could have created this kind of fractures on the surface. We don't know. There is a scenario which I like very much, is that imagine an impact on Mars. So you have seen many craters on Mars. So you imagine a big impact on Mars. So what happened? You have, again, rocks, material excavated from Mars, yes? And where do they go? They go to space, if they have enough velocity. So they go to space. So imagine the rocks, they leave Mars, they go to space, and then at some points they see Phobos. And these rocks, this is the rocks that pass through Phobos following the impact on Mars. There have been some studies about that, and I don't know if it's the right one, but at least I think it's an interesting one. So that's one of the mystery of Phobos. The other mystery is how the surface is made of, and that also we don't know very well, because to get information on the surface properties and material, we like to take a spectrum in the infrared and visible, and to try to find some absorption bands to see what is the component of the surface. And unfortunately for this kind of bodies, the spectrum, it's not that it's flat, because the spectrum has a certain slope, but there is no specific features that we could attribute to specific material on the surface. So it's really difficult to know what is the surface of Phobos. And the last mystery, which is linked to this one, is we don't know why Phobos and Deimos are there. We don't know if it's a captured asteroid. We don't know if it's created from an impact on Mars that ejected some material in space, and the material could reaccrete into the moons. So there are a lot of scenarios, and that's why it's also quite interesting. But I see that it's almost time for a break. So in fact, I will break now. I'll continue. But I can take some questions in the meantime. So, but I prefer to leave a bit of time for questions. So let's have a short, let's have the break now for part one. So thank you.